Hello my dear friends, and welcome back to the Informatics 2 class. We're going to start now lesson number 23, and in this lesson we're going to talk about recursion again. So this is the third class in which we're talking about recursion. We started last time talking about the 8 queens puzzle, and we have defined the puzzle in terms of what are the rules of the chessboard and all of that, and we introduced the concept of analyzing actually the problem so that we can somehow program it in a more systematic way. And we have introduced basically the key step outline for that. We're going to continue from there this time. So we're going to talk about the key step outline again in more details. And then we're going to introduce the backtracking algorithm as a way of looking for a solution for the problem that we have in hand. And then we're going to build our data structures, look for the most proper data structures. And this is a nice example, actually, which helps us think about the way we select the data structures, suitable data structures for a suitable problem. And then after that, we're going to get to the implementation for solving the 8 queens puzzle. Okay. So the last thing we talked about last time was this major key step in the solution, in looking for a solution for the 8 queens puzzle. And basically, we were talking about this add queen function, which is going to add a queen to the chessboard and check if that addition is a correct one, so that it will lead to a solution to the problem. All right? Otherwise, we're going to, of course, remove that queen from that position. The major steps that we have in there, in a pseudocode kind of implementation, is that we're going to look for every unguarded position, P, on the board. And as we said, the unguarded position is the correct position to where I can have a queen on the chessboard. Okay? And that means I'm not going to look at any row or column or any diagonal in which it's being guarded because there is a queen somewhere on the chessboard guarding these positions. And for that, we're going to look at all other free positions, as a matter of fact. And if we find one of those, then I'm going to place a queen at that position. And in that case, the number of queens that I have on the board are going to be incremented by 1. And then I will check, did I reach a solution? Do I now have 8 queens on the chessboard? If that is the case, then excellent. We ended up with a solution. So just display it and print that configuration. Well, otherwise, we have to add another queen to see if there are still any possibilities for adding that queen. And in here, we're calling the same function, actually, we were having on the previous slide. So I'm calling add queen again. And that means there is recursion in here. So the problem actually repeats itself again and again. Each time I have to add a new queen at a proper place, all right, and increment the number of queens that I have, and verify that this place is actually unguarded and that it is good and okay to keep that queen in this position. Well, I can add the queen to any position, unguarded position on the chessboard, and then I can proceed and add another one, but maybe I'm going to realize that I cannot add a new one. Yes, I have added the previous one in a free space, all right? However, I don't have any further free spaces to add, and I'm not done with this, solving the problem by having 8 queens on the board. So in that case, I might have to remove this queen that I just added, all right, and look for another unguarded position, another free place to where I can add my queen and search again for a proper place. So in many cases, I might need to remove the queen from position P, and in that case, I'm going to decrement the number representing the number of queens on the chessboard, and I will go back looking for another, back to the loop here on the previous slide, back to this loop to where I would look at other possibilities, other possible positions to where I can add the queen. Okay, so this is basically generally the skeleton of the program that we're going to develop to solve this problem. Let's look at this key step in depth. The sketch that we had, or the pseudocode that we just had, illustrates the use of recursion. We're going to add queens always, and that means, as we have seen in the previous slides, I'm going to call this add queen function again and again. The function calls itself actually again and again till I'm through with all 8 queens on the chessboard. Okay, so that means continue to next stage and repeat the same task, and that's what I'm doing. Once you find the proper place for a queen, okay, place it there, and then go and add another one. So that's like add queen, all right? Placing a queen in position B is only tentative, as we have mentioned on the previous slide, because simply, yes, I have added it in a safe place, free place, to where I can have the queen in there. However, when I tried to add a new queen after that, I couldn't find any proper place for that. That means my choice for this and the previous queen was not correct, and in that case I have to draw back, all right, and remove the previous queen from wherever I have put it, because that is not going to lead to a final correct solution, and I have to redo the process again by looking for another possible unguarded position. All right, so in that case, if I place a queen at position P, it doesn't mean that this queen is now in its final position and that I'm happy with it and I will reach the final solution and just go to the next step, but rather I could decide to remove it, and that's why that position is tentative only. Okay, we leave the queen in there only if we can continue adding queens until we have 8 queens on the board. If we're lucky, and if we put queens consecutively on unguarded places on the chessboard, okay, and I ended up having 8 queens on the chessboard, then that's okay. The queens are going to stay there, and that's a solution, and you just go home. That's it. The task has been done perfectly. However, this doesn't happen always, and you're not that lucky always. It depends upon where you start on the chessboard by placing the first queen and the second queen and so forth. And that's why at several instances inside the process, during this process, I might decide actually to remove some of these queens and redo the process again. So these queens are going to stay there only if I ended up having like 8 queens on the chessboard and they're all perfectly placed on that chessboard according to the rules. So the function will return, the function add a queen will return when it finds that it has finished. That means it has finished all placing all 8 queens, or when there is no further possibilities to investigate. When it gets stuck, it couldn't allocate space for all 8 queens on the chessboard, all right? Assuming that it has already, let's say, the first and the second. You started from certain position, all right? And you place the queen in there. And then you put the second in an unguarded place on the chessboard. And from there you moved, want to try adding the third one. And you kept searching, all right? And you tried to add the fourth, the fifth, but you ended up not having a solution. There is no way with this configuration. You realized, okay, the first one should not have been there to start with. I should have started somewhere else. And that means I'm going to return from this function, all right, to look for another scenario, to look for another initial setup, or maybe another position for this queen or that queen. So these are the only 2 cases to where I'm going to return from my function. A fruitful return, and that's when I have a solution, or a return like this one, when there are no further possibilities that I can examine to place new queens. So after the inner call then has returned, when I return, then it is time to remove the queen from position P. So if I return from this inner loop, and that means there are no more possible situations where I can end up with some sort of a solution, then I have to remove the queen that I have already added at position P, because if I place this at this queen at this position P, then that's not going to lead later on to a final solution to where I have 8 queens on the chessboard. So I have to draw back. I have to return back my steps and remove that queen from that position and start searching in other positions. So because simply all possibilities have been exhausted with it, there have been investigated, and these all positions are not fruitful and they're not going to lead to a solution. So that leads us to talk about backtracking algorithm. And again, backtracking algorithm means to go back and remove the last queen that you just have added, just because you have investigated all positions after that, trying to place the remaining queens, and you realize that there is no possible way to add the remaining queens on the chessboard. And that means you have to go back and remove that one because that choice was not a good choice. So backtracking algorithms attempt to complete a search for a solution to a problem. All right? And that means, given this position, all right, search all possibilities for the remaining queens. All right? And if you find a solution, then you don't have to back up. All right? You end up with a solution and your task is done. However, if you exhaust all possibilities and you realize that there is no solution, then you have to draw back to back up, all right, and then remove that queen. So what we're going to do basically, constructing partial solutions, that's the backtracking algorithm, what it means. Constructing partial solutions, so I add a new queen toward finalizing the solution, and then always ensuring that the partial solutions remain consistent with the problem requirements. That's when I add this new queen, I have to be consistent with the rules. That means when I add this new queen, it has to be placed on an unguarded position so that it can't be taken by already existing queens on the chessboard. Okay? So the addition has to be always consistent with the requirements, of course, so that as a result I can reach a solution at the end of the day. And extending the partial solution toward completion. So that's my goal, is always to construct a partial solution, maybe placing the first one, and then progress by adding the second, the third, so forth, till you get to the final solution and to a complete solution to the problem in hand. When an inconsistency occurs, when there is a problem to where I try to break the rules that I have, then the algorithm backs up. And that's where we backtrack. How do we back up? Well, by removing the most recently constructed part of the solution, this last portion that you have added to the solution has to be undone, okay? And try another possibility. So it's like building your house to where you add bricks on top of each other to get to the final house that you want to build. All right? So you start from the first one, looks okay. All right? You try the second one. Is there a possibility of having a second one on top? Yes, sounds good. So you proceed. Each time you're adding partially to your solution toward building the whole thing. Well, now you're realizing here that no, you can't have this brick in here. Okay, because otherwise you're not going to have a window, you're not going to have a door or something like that. Then you have to backtrack and remove the last portion that you just added, just because after that you're not going to end up with a window for your house, and it's not going to be a nice thing, and it's not going to be a perfect solution in your case. And in our case, when for the 8 queens puzzle, okay, the partial solution is adding a queen, one queen on the board. Okay. So I start with adding 1, that's a partial solution, and I try to build on that partial solution by adding the second one now, okay? And after I add the second one, I start searching for possibilities for the third one, and so forth till I reach to the 8th. If I could manage to get to the 8th, then everything is fine and I'm through, right? And I can just display the configuration as a solution to my problem. However, if I realize that going to the 3rd, 4th, and so forth to the 8th is not gonna be fruitful, okay, that means the position I selected for the second one was not really a good choice, and that's why I have to backtrack and remove this second partial solution. Okay, and then I will try to look for another possibility. Backtracking proves useful in situations where many possibilities may first appear, but few survive further tests. This kind of algorithm, this backtracking, is actually very helpful when we have plenty of choices to select from. However, not all of them are actually correct. Not all of them are going to lead to a correct final solution. So what we do is we attempt one of the proposed solutions, okay? So I select it, and then I investigate it to see if it helps me or not. If it helps, that's excellent. If it doesn't, then I have to backtrack and deselect this solution and maybe look for another possible solution instead and examine it again and so forth. So whenever I have different possibilities, then an algorithm like this is actually very helpful. Does it help in our case? Well, yeah, sure. We have so many possibilities because when I place the queen, let's say somewhere on the first row, then I know the remaining 7 queens are going to be placed on the remaining 7 rows, of course, but I don't know at which column each one of them is going to be. So I have many possibilities on the second row, either the first position, second, up to the 8th. Right? So these are the possibilities, and I have to try one of them. Maybe 1 or 2 of them are going to be guarded just because I have the queen on top guarding them, something like this. Very quickly, I'm not going to draw the whole chessboard. Okay, assume that on the first row, I have placed the queen in here, let's say, and then now in the second row, all right, I have this possibility. I can't use this, can't use this, can't use this because same column or diagonal. This is a possibility, this is a possibility. So where do I put the second queen? Here, here, or maybe the rest of the positions, as I don't have all 8 of them in here. All right, so I have to investigate all of these possibilities. All right, for the second one, putting the queen in here is okay. Here is okay. Here is okay as well. But I don't know about the remaining now queens, because these are going to depend on the position I'm going to select in here. So I don't take things partially, but rather I will investigate every possibility, all right, trying to reach to a final solution, all right? And if this was fruitful, then I'll take it as a solution. If, however, I realize that I cannot end up with all 8 queens like that, then I have to backtrack and remove from here and maybe investigate this position or this position and so forth. Now choosing the data structure. Well, selecting the data structure is actually depend on the nature of the problem we have. The problem in our hand talks about the chessboard, right? And the chessboard, as we all know, has 64 places, an 8 by 8 kind of thing, square. And that's why, basically, I'm going to use an 8 by 8 structure, maybe, to represent the different positions that I have in the on the chessboard. So one possibility, and this is the straightforward way of thinking about it, is to consider an 8 by 8 integer array to represent the chessboard. Well, why integer? Why not Boolean? Let's say, yes, there is a queen, or no, there isn't a queen. Well, we need an integer because each entry in the array of this 8 by 8 array denotes the number of potential queens guarding the position. Well, I need, to identify whether the position is guarded or unguarded. And now, on the chessboard, I need to know how many queens are guarding. I'm just drawing a little piece of this chessboard, okay? Let's say this position, okay, with I and J in the 8x8 matrix that we were talking about in here, okay? So how many queens are guarding this? This depends upon how many queens are already actually on the chessboard, let's say, here and here. And in this case, this one is guarding this position. This one is guarding this position. Maybe if we have one here, let's say, then this one is guarding this one. So I will have 3 in here. And this helps me a lot. Okay? Thus, to add a queen to any position, we increase by 1 the count for each position on the same row. So when I add a queen to the board, I'm gonna go to all entries guarded by that queen along the same row, along the same column, along the same diagonals, and increase all the entries in there, the count in there, by 1 to indicate that it's guarded by 1 more queen now. All right? To remove a queen, if I, let's say, backtrack and decide to remove that queen, that means I'm gonna go to all positions along the row, along the column, main diagonals, and decrease the entries in there, the count in there, by 1, simply because it's not guarded anymore by this queen because it has been removed. Okay? A position then, according to this definition, is unguarded if and only if the count it has at that particular position is 0. 0 in there means there are no queens guarding this. So to add a queen then, at certain position, that position has to have a count of 0. Excellent. Let's look at this very well-known pigeonhole principle. This pigeonhole principle is very well known, as a matter of fact. And it says, if you have n pigeons, and you have n pigeonholes, and no more than 1 pigeon ever goes in the same hole, then there must be a pigeon in every hole. Very basic. True. n pigeons, n pigeonholes. No 2 can go to the same place. That means every pigeon has to pick one of the holes. True. There are enough holes for all the pigeons that I have. Well, it sounds very simple and very basic, okay, but it's very important when we understand this. How to utilize this principle in our case, all right? As with the pigeonholes, there can never be 2 queens in the simply because once I put in a row, that means all positions along that row are guarded, simply because they can be taken by that queen. True? So basically, I have then 8 different rows. And if I can only have 1 queen per row, and I have 8 rows, I want to place 8 queens. That's basically the n pigeons going to n pigeonholes. I have 8 rows resembling pigeonholes, and I want to place 8 queens, pigeons basically. So there has to be a way to place all of these 8 queens on the 8 rows. Fantastic. That's how we're going to utilize then this principle. The goal is then to place 8 queens. Only 8 rows are available. Thus, 1 and only 1 queen per row. So that means once you place a queen on a certain row, forget the rest of the cells in that row because they're not part of your solution for sure. So then we're going to use something like a 1D structure data array called column, basically of type integer, to refer to these actually different 8 rows that I have. And in this column of 8, what I'm gonna have in there, let's say column I, this says that the column containing the queen at row I is this. So something like, if I say column of 3 equals 6, this means that the queen placed in the third column, in the third row, is at column 6. And this is enough to give a whole picture of the entire chessboard, right? So again, this says I have a queen at the third row. And where exactly on the third row? It's in the 6th column of that row. Further, we need to keep track of whether each column is free or guarded. I need to look at the columns. I need to check which diagonals are actually free and which are guarded as well. Well, how to implement this? How to know how to look at the columns and the diagonals? I know about the rows in here, so it's done. All right? But how about these? Well, for that, we're going to use 3 Boolean arrays. These arrays are column free or col free. It's basically of type Boolean, which says yes or no, and it checks whether a certain column is free. So if that column is free, then I'm going to have a true in that column. Otherwise, I'm going to have a false value. Up free. And this talks about the diagonals from the lower left corner on the chessboard, lower left, up to the upper right. So it talks about diagonals that go this way. It's called up free. So again, each of these positions actually are going to be examined, all right, to see if they are guarded or unguarded, true or false. All right. And then the third one is the what's so-called down free. And it's for diagonals from the upper left, up here, down to here on the chessboard, the lower right. Okay? The size of col free, it talks about columns. I have 8 columns. However, for these, they can grow up to 15 actually as maximum. And that is columns plus rows minus 1. Okay. A position Q is then guarded if Q equals to P. All right? That is a new position and the previous positions are on the same column. So if the new position is on the same column like the previous one, then that's guarded. Or if Q is on the same diagonal as P. All right? So if it happens that I already have a queen in here, and it happens that the new queen is going to go along this one, then definitely this position is guarded and I cannot have then a queen on that place. How to identify positions along a single diagonal? Well, it depends. Along the main diagonal, downward, from here to here, positions are 0, 0, 1, 1, 2, 2, 3, 3, up to 7, 7, right? So basically, the row and column indices are always the same. Or saying that in a different way, always row minus column equals to 0. So that identifies the up, down, this one, diagonal, main diagonal. Along any other downward diagonal, not necessarily this main one, all right? Any other diagonal, if you make the look deeply into the numbers of the columns and rows, as a matter of fact, we're going to realize that I'm going to always have a constant difference when I take row minus column. Always constant. Okay? So that's a way of knowing whether I'm on the same diagonal or not. And this difference ranges from when I have in here row 0, column 7, that's 0 minus 7 in the upper left corner, up here, down to 7 and 0 in the lower corner, lower left corner, down here. All right? Similarly, along upward diagonals, the sum is always constant. So when I'm here, it's going to be 1 plus 0, 7 plus 0, or 6 plus 1, and so forth. On any other diagonal, if we investigate these numbers, we're going to realize always that I'm going to have always a constant sum of the row and column. So that's another way of checking for up diagonals. So they start from 0 plus 0 to 7 plus 7. That goes to 14. Implementation. Knowing all of this, we're going to talk now about the implementation, and it's very simple and straightforward if we absorb and digest what we have covered so far. It's called 8 Queens program. Prerequisites none, and post condition all solutions to the 8 Queens puzzle will be printed on the screen. The uses, I'm going to definitely use this add queen, which we talked about in a skeleton form at least, and we're going to rewrite it. And write board, we're not going to implement this. It's simply to just print on the screen the solution. That's very simple. Okay, the main program starts with include common.h, and we're defining the board size 8. And then we're defining diagonal to be 2 times board size minus 1, and that refers to the maximum diagonal size I could have, which is 15. And we're defining the down offset to be 7. All right, we're using this function, write board and add queen. Basic definitions. I'm defining queen column, and that's the column thing, which refers to which column that the queen is located for a particular row, and it's of size 8, board size. The Boolean column free of type of size diagonal, and this gives me tells me which column is free, and Boolean up free of size diagonal again, and this tells me the up diagonals whether they're free or not, true false thing. And there's the third Boolean function down free, talking about the down diagonals, these diagonals, and it's of this size, and again it's of type Boolean to tell me whether the down diagonals are free or not. And then I'm going to start with the queen count, number of queens that I have, and I'm initializing this to -1 because for the backtracking algorithm I could start from 0, but this is just for precaution. So row whose queen is currently placed. So I'm going to start with row -1 because I have row 0. It means something because we always start from 0 in C. Okay, integer, number of solutions so far equals to 0. Okay, and I'm going to increment this as we find a good solution and we display it on the screen. Okay, and here goes the main. Integer I, I'm going to use this local variable as an index to my major loop. And this major loop goes basically from 0 to 7, 8 actually, but less than 8. That means looking to place all 8 queens on the chessboard. All right, and I'm initializing column free to be true. All columns at the beginning are free. All diagonals are free, so true. All downward diagonals are free, true. Okay, so that's just the initialization. And then I call this function add queen. And this add queen, as you know, is going to call itself again and again. Each time it adds a new queen, basically it's going to investigate the rest of the queen positions, and if it finds a solution, it's going to display it. Otherwise, it's going to backtrack. All right? And if I return successfully from here, then I'm going to return with a 0, indicating that this is a fruitful result. Otherwise, I will have another return from the inside the queen, add queen itself. Okay, so what's important is actually the add queen function. That's what it has, the details. This is just in the main program, we just have initialization. Add a queen, it adds a queen to the board recursively. And the preconditions, queens have been properly placed in rows from 0 through queen count. So far I have added queen count queens on the board. Okay, and I want to add the next one. So the assumption is that all previous queens have been added correctly according to the rules. All right. Post condition. Well, the post condition, all solutions beginning with this configuration have been printed. So all solutions will be printed to the screen. Queen count and all other values that we have used for our arrays and this add function are going to be initialized. Like the column free, diagonal free, up and down, return them back to the initial state of true. Usages, we're going to use the global variables queen count, and this is a global variable which counts the number of queens that I already have on the chessboard. Global arrays that I have already defined, like queen column, column free, up free, down free, and the function right board. Okay, let's see the implementation. Void add queen doesn't take anything, and it defines a local variable called column. It's going to add a queen, so right away it's going to increment the counter, which indicates the number of queens that I have on the chessboard so far. And then I'm going to say for column equals 0 to board size, that's to 8, of course less than 8, 0 to 7. Each time what am I going to do? Well, I'm going to check if column free at this particular column, if it's true, and the up diagonal is free and the down diagonal is free. That means I'm checking that position at this particular column. Is it unguarded? So to make sure that it's unguarded, it has to be unguarded, 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 true and true and true. If that is the case, then okay, this is a good place to put your queen in. So put a queen in this position, which is and a queen count and column. All right? So queen column at this queen count equals to column. That means the fifth queen, let's say, if I'm adding the fifth one, is going to be at this particular column. All right? And then I'm going to go to that location in the columns, all the column, make it false to indicate that it's guarded now. Go to the up diagonal, make it as false because it's guarded now. And go to the down diagonal and make it false as well. All right? And now, if queen count equals to 7, that means I have from 0 to 7 now, I have added all the queens, then basically I'm done. So what I'm going to do, just, and this is my terminating condition, go and display the result on the screen. Otherwise, I'm going to call again the add queen. And basically, it's going to go through the same thing again and again. So, and in that case, I'm going to make this available, and this available, and this one available. And that's why when I'm backtracking, actually, because I did not find a solution, actually, and this that means remove that queen and make these places available and discount or decrease the number of queens that you have by 1 because you already added that one. Okay? It's pretty simple, straightforward. And it solves the problem nicely using this recursive algorithm. Actually, if you try to do it the iterative way, it's going to be a tedious, long task. All right? So it's a very good example on doing this kind of thing. Well, thank you very much for watching. This is all I want to talk about. And if you would like to see this material on the internet, you can definitely go to the UNINETTUNO website. And keep a smile on your face in that case. Click on the UNINETTUNO project, and you're going to find lots of interesting stuff. Bye-bye.